Assalamu alaikum.
Walaikum salam, sir.
Okay, so welcome to the class of microwave engineering. Okay, so before I start my lecture, is there any question from previous lecture? Any
No, sir.
question from previous lecture? Okay, in case there is no question, so let me start today's lecture. So in last lecture, we introduced the concept of losses in the transmission line, and we consider a lossy transmission line, which we called as low loss transmission line. Okay, because in a practical situation, no one is going to use a transmission line which has too much losses. So we can analyze a lossy transmission line, assuming that losses are small, and that line is known as low lossless line. And we let me just summarize regarding low loss line. So what we concluded last time was that if there is a low loss line, then its attenuation constant is computed using this expression 1 by 2 r c by l under the root plus g l by c under the root. This is the attenuation constant in units of Nepers per meter, and phase constant of low loss line was, again let me put the approximation sign, this is approximated equal to, so beta is equal to omega times LC under the root. And we also found that the characteristic impedance of low loss line is also approximately equal to L by C under the root. In comparison to lossless line, attenuation constant is exactly zero, phase cons is exactly equal to omega LC under the root, and characteristic impedance is exactly equal to L by C under the root. So if you compare low loss line with a lossless line, it is obvious that the phase constant of low loss line is approximately equal to the whatever is the phase constant of lossless line. And characteristic impedance of lossless line, which is exactly L by C under root, but for low loss line, we can also use the same equation for Z naught as well. But the major difference is for a lossless line, attenuation constant is zero. There are no losses on a lossless line, which is an ideal line. But for a practical low loss line, attenuation constant will not be equal to zero. It will be equal to this expression. So depending upon how much is the resistance per unit length, capacitance per unit length, inductance per unit length, and conductance per unit length, you will get some finite value out of this expression. And that will be the attenuation of that line. Now, there is a related concept of distortionless line. So let me introduce this term as well. Distortionless transmission line. So we all know that a distortion is something which is undesirable. So first of all, we need to define properly what we mean when we say that there is distortion. Okay. So if there is a transmission line and on the left hand side you connect a signal or you want to transmit some signal that is input signal, so that signal will travel to this transmission line, and at the right side or at the output of this transmission line you will get an output signal. Now how much this output signal is equal to input signal. Okay, so in ideal situation we want that the output signal, its shape should be exactly equal to the input signal. Whatever is the shape of the input signal, I want that output signal should also have the same shape. But that can only happen if this transmission line is distortionless. If it is not a distortionless line, then what will happen? That output signal will be different from input signal. Or we will say that this transmission line has distorted the input signal. Now, why any line will distort the signal? Why output signal may not be same as input signal? What is the underlying concept behind distortion? The distortion is due to phase constant. Okay, so if phase constant, which we are representing with beta, if beta is a linear function of frequency, then there will be no distortion. Now, what is the mathematical representation of this statement? When I'm saying that beta is a linear function of frequency, so what I'm actually saying is that beta has to be equal to some constant, let me call it k, into, or let me use some other symbol because we already using k as a symbol for phase constant. So let me use a times omega. So what is this a? A is some constant. So when I say beta is a linear function of frequency, this is what I mean. So beta is directly proportional to omega. If transmission line phase constant, if it fulfill this criteria, then it will be a distortionless line. So it means if there is a if the output signal is distorted, then the transmission line is not fulfilling this criteria. Now, if you go back for a lossless line, if you look, beta is a linear function of omega. Beta is a linear function of omega because LC under root is some constant. So LC under root, you can say this is what A is. Okay. So we can say that all lossless transmission lines, they are distortionless lines because beta is a linear function of omega. Similarly, because low lossless lines, their phase constant is also approximately equal to omega times LC under root. So again, you can see that beta is a linear function of omega. So low lossless line is also distortionless line. But if you remember, the general lossy line, any general lossy line, the propagation, phase constant, sorry, the complex propagation constant of any general lossy line is mathematically represented by this representation, which we have derived and which we have been using throughout this course. The actual expression of propagation constant is this, and this expression, if we are able to separate the real and imaginary part, then we know that the real part will be alpha and imaginary part will be beta. So in this case, if you somehow, if you simplify this so that you can get alpha and beta, you will find out that beta will not be a linear function of frequency. So let me write it down. In this case, beta will not be a linear function of omega. It means what I am actually saying is beta will be proportional to either omega square or maybe omega cube or something like that. So it means general lossy line, because beta is not a linear function of omega, as a result, it will be distorted line. Or I will call it not distorted. Let me use some more technical term. So what I'm saying is this line will introduce distortion in the output signal. There is a further explanation of distortion. So why, if beta is a linear function of omega, there will be no distortion. And when beta is not a linear function of omega, then there will be distortion. So I can relate this distortion idea to phase velocity. If you remember phase velocity, which we derived, and we found that phase velocity on a transmission line is always equal to omega times omega divided by beta. So when beta is a linear function, so when beta is a linear function, so there will be some constant multiplied by omega. So what will happen? Omega will be cancelled out. So as a result, phase velocity will be a constant number. So what type of behavior distortionless line will show? On a distortionless line, the phase velocity will always be equal to some constant. So irrespective, it doesn't matter what is the frequency of this signal. Any frequency signal, when it travels through this line, its phase velocity will be same. So it means if we, whenever we talk about some signal, so actually this signal is not just one frequency signal, it is some kind of a wide band or broadband signal. So it consists of number of frequency. It consists of number of frequencies. So When you talk about a signal, so actually it is a wideband signal. It consists of number of frequency components. So when all frequency components, their phase velocity is same, so it means all frequency components will arrive at the output at the same time. And that is the reason we get this no distortion behavior. All frequency components arrive at the other end of the transmission line at the same time. So as a result, there is no distortion. But when beta is not a linear function of omega, so you can clearly see if beta is, if let's assume that beta is if beta is, let's equal to some constant into omega square. So now beta is not a linear function of frequency. If we have this type of behavior, so what will be the phase velocity? Omega times beta, and then omega divided by a times omega square. So this will cancel out. So you can see Vp is equal to 1 over a omega. So now you can see we cannot say that phase velocity is constant. Phase velocity is now dependent on omega. So if omega changes, phase velocity will change. So for a wideband signal, which consists of number of frequencies, so each frequency component will travel with a different phase velocity. As a result, it will appear at the output at different times. So what will happen to this wideband signal when it travels through this line? If this is if this is a distortionless, if it is not a distortionless line, so what will happen? Different frequency components will appear. They will reach at the other end of the transmission line at different times. So as a result, we will have distortion. So now you can also relate distortion to phase velocity. If phase velocity, if it is constant on a transmission line, then it means it is a distortionless line. And if the phase velocity is a function of frequency, then it means the transmission line will not be distortionless line. Now with this concept, let's consider another possibility that if we are having a general lossy line, which is having a propagation constant like this. So in this situation, beta will not be a linear function of frequency. But there is one possibility if we design our general lossy line in such a manner that it's fulfill this criteria. So let me use the criteria. If if uh, if for a lossy line, resistance per unit length divided by inductance per unit length is equal to conductance per unit length divided by capacitance per unit length. If the ratio of R by L is equal to G by C, then we get a distortionless line. So let's verify this condition. What will be the effect of this on phase constant? Because right now we have related the distortionless line to this condition. Which condition? This one. If beta is a linear function of frequency, then there will be no distortion. And no distortion means distortionless line. So let's find out with this propagation constant, if we can prove that under this condition, beta is a linear function of frequency, then it will mean that we are having a distortionless line. Okay, so let me prove this. So propagation constant for a lossy line is equal to this. I can rearrange this equation by Let's say taking j omega L as constant from this term and then j omega C as common from this one. So what you will get? So propagation constant will be equal to j omega L 1 plus R divided by j omega L j omega C 1 plus G divided by j omega C whole under the. So this is the same expression, but I'm just rearranging it by taking this term as common and by taking this term as common. So you will get this thing. Let me bring this term and this term outside of the square root. So you get j omega L C under the root. And inside the under root, you will get this thing. So this is L. Then you can multiply these two complex numbers. Just multiply these two complex numbers together. So propagation constant will be equal to j omega LC under the root. And we will get 1 minus j R divided by omega L plus G divided by j omega C, not j omega C, sorry, only omega C minus R G divided by omega square LC. So what I have done is I have taken this general form of complex propagation constant, which is R plus j omega L into G plus j omega C under the root, and I have rearranged it to this form. So this is the same thing, but represented in a different manner. Okay. Now let me put this condition. I mentioned that if we design a transmission line which is lossy, but we design it in such a manner that the ratio of R by L is equal to G by C. So let's put this condition. So what I'm going to do is I'm going to replace G by C by R by L because they are equal. So wherever I have G by C, I can replace it by R by L. So what will happen to this expression? So this G by C that becomes R by L. So you get 2 times R divided by omega L. Similarly, in place of G by C, you put R by L. So you get minus R square divided by omega square L square under the root. Now this under root term is basically j omega LC. It is basically 1 minus j R divided by omega L whole square. So if you expand this 1 minus j R omega L whole square, you will get these 3 terms. So this under root and this square will cancel out. So we get simply j omega LC under the root into 1 minus j R divided by omega L. Let me multiply this term. So what you will get? You get propagation constant is equal to So 1 multiplied by this, you get j omega LC under the root. And you multiply this, so minus, and then j and j square, you get another minus. So this minus will become plus. So you get plus. And then you have omega. So this omega and this omega will cancel out. Then also you have L under root and you have L over here. So if you simplify this, you will get this result. That is plus R L by C under the root. So this thing multiplied by this thing will give you this term. So now you can clearly see this is propagation constant. And we mentioned that this propagation constant has a real part and imaginary part. And based on this simplification, what we know, this thing, j times this thing, this is beta. So this something is beta. And this is a real number, so it must be alpha. So for this line, attenuation constant is equal to R L by C under the root Nepers per meter. And its phase constant is omega LC under the root. And you can clearly see beta is a linear function of omega. Therefore, this transmission line is going to act as a distortionless line. And this is what I started with. That if you have a transmission line which fulfill this criteria, then we get a behavior that is transmission line will act as a distortionless line. Now, once we have introduced a lossy behavior of transmission line, let's talk about the effect of termination. So now we are going to talk about the same idea when we use lossless line and we terminate it with a load. So depending upon whether load is matched to the line or whether it is not matched to the line, we get different behavior. So let's consider the same situation for a lossy line. So now I'm going to talk about the terminated lossy line. So now when I will draw a symbol of transmission line like this, and I will again assume that it is placed along an axis, and in our case, this axis will be Z as before, and we will connect. So this is a lossy transmission line. So now I will represent this transmission line by representing its characteristic impedance Z0. I'm also going to represent that it is having alpha as well as beta. So whenever you draw a symbol for a transmission line like this by representing alpha as well, so this directly means that you are talking about a lossy line. And now we are interested in finding out the voltage as a function of position and current as a function of position on this transmission line when it is terminated with some arbitrary load, ZL. As before, the load, we will assume that the point at which load is connected, the value of Z is 0. And if transmission line length is, let's say L, small l is the symbol that I'm using for representing the length of the transmission line. So at this point, which is kind of an input, so at this position, we know that Z will be equal to minus L. And this is the point at which we will connect our source or generator. So how much in impedance will be there, we will represent it with Zn. Now, what will be the expression for current and what will be the expression for voltages and current? So we already derived this concept before. So voltage is going to be represented like this. V naught plus, and now we are going to write down e power minus gamma z plus reflection coefficient at the load e plus gamma z. So when we solve wave equation for a lossy transmission line, in that particular topic, we derive that voltage as a function of position will be according to this expression. And now, if you compare it with a lossless line, so in case of lossless line, in place of this term, we used to have e power minus j beta z, and we used to have e plus j beta z. But now, because transmission line is lossy, so we cannot use simply beta, because now we also need to include alpha as well. So alpha and beta is means we have gamma. And this term is representing, as before, the forward wave, the wave or signal that is traveling towards the load. And this term is representing a wave or signal that is traveling in this direction towards the generator. And similarly, current expression is V naught plus divided by Z naught e power minus gamma Z minus gamma e plus gamma Z. Correct this symbol. So where gamma is complex propagation constant equal to alpha plus j beta, and this gamma is voltage reflection coefficient at load position. Now, once we have general expressions for voltages and current, we can find out other parameters as well. So this reflection coefficient, and I have already defined it when you just use this symbol. So this symbol is used to represent the voltage reflection coefficient at load position. So right at this point. But I may be interested in finding out how much is the reflection coefficient at this point, at this point, at this point, at this point. So I at each and every point on the transmission line, reflection coefficient will have its own value, and it is not going to be represented by this symbol. So using the same idea, that what is the general definition of voltage reflection coefficient? The general definition of voltage reflection coefficient is it is the ratio of reflected voltage wave divided by incident voltage. Okay, so based on that definition, I can write down that reflection coefficient is the ratio of reflected voltage wave divided by incident voltage wave. And mathematically, reflected voltage wave is represented by V naught minus E plus gamma z divided by incident voltage wave, which is represented by V naught plus E power minus gamma z. So this is clearly telling us that this propagation constant, it is function of z. So I should be better representing reflection coefficient as function of z. And of course, z means position. At, when I move along transmission lines, so actually I am changing z. Okay. If I further simplify this, so you get v naught minus divided by v naught plus, and I can bring this e power minus gamma z to the numerator. So it becomes e power plus 2 gamma z. So this is the general representation of voltage reflection coefficient as a function of z. Okay. Now with this general expression, now I can come back and I can find out if I'm interested in finding out the reflection coefficient at this position where we have connected our load. So at this position means z is equal to 0. So let me put z equal to 0 over here. So at z equal to 0, this reflection coefficient will be simply equal to v naught minus divided by v naught plus. And now you can refer back that when I introduce this term over here, when I've just used gamma without uh, representing it as a function of z. So this gamma was a reflection coefficient at load position. So in this expression, when you don't use any brackets and as a function of z, so it means by default, this is the reflection coefficient at load position. And now we know that this thing in the general expression, when z is not equal to 0, this term can be replaced by this thing. So I can say v naught minus by v naught plus is basically gamma of 0, e power plus 2 gamma z. And using the standard nomenclature, I will say gamma z is equal to gamma e power plus 2 gamma z. Because as I mentioned before, just writing gamma means I'm talking about this thing. Let's continue this discussion in the next session. So this is the result.